Hello, this is Josiah Winslow recording for his Programming in Java course at MATC for instructor Mark Cribb. Now this is not an assignment video, this is a supplementary video to an assignment video because I don't want to make that video too long. We have a new assignment, Assignment 5, and for a few of our challenges we are asked to do some text processing work because text processing is an entire one of our chapters. So after I got done with those, I wanted to do more research on what a char even is in Java, because, well, it's a character, but what does that even mean? Well, I found out that in Java, a char is a 16-bit unsigned integer that represents a UTF-16 code unit. Now, what does that all mean? Well, UTF-16 is an encoding scheme or encoding method for Unicode code points. And a Unicode code point is basically one of the most objective things that you can call a character. Most strings in most programming languages you'll ever come across are groups of Unicode code points. Now let me show you what I mean, because I made some visual aids. And I spent way too long on them, so I hope you like them. So this is a typical Unicode code point. It's got a hex value of 26 and it represents an ampersand. Looks like that. Now, there are different ways that you can represent this. You can represent it as the code point itself, but also if you're wanting to turn that into some sequence of bytes, there are different ways. Here are 3 of them. In UTF-8, the code units for that are 8 bits long, or a byte. And for an ampersand, that byte is going to be hex 26. In UTF-16, it's the same story, except there are 16-bit units. And this, by the way, corresponds to a char in Java. So it's going to have a value of 26, but in 16 bits. And in UTF-32, which uses 32-bit units, it's still 26, but with 32 bits. So this seems simple enough, right? Well, as you get past all the characters that exist in Unicode, eventually you're going to get outside of the range of a byte, and you are going to need to store even more characters with even longer byte sequences. For example, here is the Greek small letter theta, which has a code point value of hex 3b8. Now in UTF-8, it's encoded like this with 2 bytes. In UTF-16, this is also 2 bytes, but it's 1 code unit still, because 3b8 fits into a 16-bit number. And in UTF-32, which, by the way, every code point that exists in Unicode can fit into a 32-bit number, even though most of the time it's going to waste space because of all of the 0 bytes at the beginning. In UTF-32, it's 0000003b8 to represent this character. And if you keep going farther and farther than that, you'll get outside the range of a 16-bit number, and so you'll have to start using 2 UTF-16 values to represent a character. For instance, this is the very polarizing emoji, faced with tears of joy. Now, it's got a code point value of hex 1F602. Now, in UTF-8, you need 4 bytes to encode all that. In UTF-16, you need 2 16-bit numbers. And in UTF-32, you still need 1 number, because that's how powerful UTF-32 is. Now, if it stopped there at 1 code point per character, that would be grand, and that would be very simple for text processors to handle. But there are some characters that take up more than 1 code point. And here's an example. So, the flag of the United States looks very singular, right? Looks like it's a thing, looks like it's one thing. It doesn't have its own Unicode code point. What it has 2 regional indicators. regional indicator U, regional indicator S. And those are a country code. So what Unicode decided to do to represent flags is it reserved 26 of these regional indicators, one for each letter, and it gave every country a 2-letter code. That gives it 676 flags with only 26 code points that it's using for all of them. And here are the representations for those in the different encoding systems. As you can see, it needs 4 chars to represent 2 code points, 8 UTF-8 bytes. And there are even longer sequences of characters that need more than 1 code point to represent them. Case in point, here is a family emoji that consists of a man, woman, and boy. Now, this is actually literally the emojis for man, woman, and boy joined together with something called a ZWJ, or zero width joiner. And here are the different pieces of data used to represent that in the different encoding schemes. As you can see, it needs 8 chars, 5 code points, 18 UTF-8 bytes. And, by the way, these kinds of sequences can get really crazy. This is the last one I'm going to show you. But, here is a kiss between a woman and a man with light skin tone and a dark skin tone. Now, this is the longest zero width joiner sequence that I was able to find for any emoji that is supported by Unicode. And what this is a combination of 10 different code points. And in order, they are woman, emoji modifier Fitzpatrick tone 1-2, zero width joiner, heavy black heart, variation selector 16, which tells the heart to render as an image instead of text, zero width joiner, kiss mark, zero width joiner, man, emoji modifier Fitzpatrick tone 6. And as you can see, the data that is used to represent these are really, really unwieldy. You need 15 different chars, 10 different code points, 35 different UTF-8 bytes. And as if that doesn't make processing text hard enough, that some glyphs happen to be multiple code points, which sometimes even happen to be multiple chars in Java, and even JavaScript works like this when it wants to. There's varying support for actual Unicode code points in most of these languages. But anyways, as if that doesn't make text processing hard enough, it gets even worse with actual text, if you can believe that. In 2015, there was actually a very popular bug in iOS that was termed effective power. And what it was if you sent a text message that consisted of the words effective power plus some random string of Arabic to an iPhone, then whenever the iPhone received that, it would crash. It wouldn't even really have to open the messaging app. It would just need to try to show up in the notifications bar, and it would just crash the phone. And what happened was, so in the notifications bar, if the message is too long, it has to cut off at a certain point. And it decides where to cut it off and then places 3 dots after it for an ellipsis to let the user know, hey, the message continues inside of the messaging app. But there are certain strings in Unicode, and the language used here was Arabic, but there are certain strings of code points that will visually render as longer for a shorter cutoff string. So at the point that it decided to cut off that string, and then it placed the 3 dots, the string was longer than 1 line, which iOS didn't expect, and then it would crash. So, long story short, text processing is really, really hard. And, by the way, after finding out what a Java char corresponded to, I realized that had implications for the projects that I was working on, the programming challenges that I was given. So, if you are a student and you are working on these, go off of this video now before you get spoiled as to how I do these challenges. You have 5 seconds. 5, 4, 3, 2, 1. Too late. So, right here I am going on tio.run, which is an awesome website that you can use to run code in almost any language you can think of. There are 260 different practical languages and 420 different so-called recreational languages, of which you can choose one and you can start writing code. For example, if I want to write in Java, I choose Java, and maybe I can load the Hello World example, and hey, would you look at that, it prints out Hello World. That's amazing. So yeah, if you ever want to quickly run a piece of code in any language, go to tio.run. It's neat. So, one of the challenges that we were given is to reverse a string. Now, the naive way to do that is to go through the string backwards and keep appending the chars that you see to a new string or a new string builder. I chose string builder in this example. And so this will reverse the chars of the string. It'll reverse the different UTF-16 code units. But it might take more than one UTF-16 code unit to represent a Unicode code point. So, for example, if I typed in LMFAO face with tears of joy, who did this? And then I pressed enter, it would print it backwards, except these two characters, it's a question mark because Java doesn't really know how to give it to us, because these two, by the way, represented the 2 different UTF-16 code units that were used to display this emoji. And if you reverse them, it makes a sequence of UTF-16 code units that doesn't really make sense. So how would you fix that? Well, it turns out that that's actually a native function of string builders. Your book won't tell you this, but if you go online, it'll tell you all about it, and your IDE will tell you about it if you try to type it. You can append the string to a string builder, and then run the reverse method on the string builder, and then convert that to a string and return it. And this works for not only real strings, any old strings, but also it works on Unicode code points, and it preserves them when reversing the string. And there we are. Now, as a consequence of that, though, it also kind of breaks up the zero with joiner sequences that I told you about. For example, here is family with man, woman, and boy. And when it reverses it, it'll reverse those sequences of code points, and it'll turn into boy, 0 with joiner, woman, 0 with joiner, man. Which becomes this. So if you did want to preserve that, you'd have to be smarter about it. But yeah, this is way better than even the naive method, because let's run this in the naive method too. Yeah, it's still a bunch of question marks. And by the way, you want to know something interesting about this? Is that because Unicode flags are actually 2 code points, if you reverse them, then you might end up with with another flag that is the sequence for one flag reversed. For example, for the US flag, it doesn't actually give a real code back, so it gives us a SU right there, which the code for the US flag is US. So that's not a real flag, but let's say we were working with the Great Britain flag. Right there, the Union Jack. And we tried to reverse it by code point, we would get the flag for Bulgaria, because the code for this is GB, and the code for this one is BG. And let's use one more example. The flag for the United Nations. Right there. If we reverse this with the code UN, if we reverse it, then we'll get a flag with the code NU, which is the flag for a small island country called Niue, I believe. Niue. Niue. So, yeah. I think it's pretty interesting to look at this. And by the way, if you were to do this in the naive method, I'm working with the naive method right here. You get question mark, and then you get like a sensical letter in the middle. Because the code points, not the code points, the code units for the regional indicators all start with the same 16-bit word. And so this is the second part of the N, then the first part of the N, then the second part of the U, then the first part of the U. And that makes this. I think it's pretty interesting. And there was another challenge that we were given that is trying to sum the digits of a string. So here I've got a method that initializes the sum to 0, and then for each char in the string, if that char is a digit, then it gets the numeric value of that digit and adds it to the sum. And then once you run that, that should work. For example, if I did 314159, then it'll return 23, which is in fact the sum of the digits. However, there is a different way to do this that relies on something that I said at the very beginning about chars, if you can remember it, and that is that they are 16-bit unsigned integers. That's right, Java actually considers these things as integers. That is what they are, that is how they're represented. You can even literally do math with them. Which is a game changer, because what I figured out that you can do is... So here is where I check whether or not it's in the range 0 through 9. So the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are sequential in the list of Unicode code points. So if the character is less than the code point for the value for 0, and if it's greater than the value for 9, then it's not a digit, and we can go to the next character to try to see if it's a digit. But if it is a digit, then we can get the numeric value by doing the character minus the character for 0. And that will give us the right value for it, starting from 0 at 0. So this will also work if we try to do it. 23. There we go. And all of that relies on the knowledge of what chars are and also how to deal with them as far as Unicode goes. So, yeah, I just wanted to share that info because I had no one else to share it with, and I thought it was pretty interesting. And if you want to solve these using that sort of method that I'd been using for those, you can go ahead, knock yourself out. So, yeah, take care.